Hi, welcome to Educator.com. My name is Will Murray, and we're going to be starting the probability lectures today, so thanks very much for joining us. We're going to jump right in. We're going to learn some terminology in this first lesson. We're going to learn about experiments and outcomes and sample spaces and events. So let's get right started with that. The words that we're throwing at you are all kind of used to describe probability experiments. So let me first introduce the word experiment itself. An experiment is a process leading to exactly one of various possible outcomes. So we'll see lots of examples of this as we go through the lectures, but some examples to keep in mind. What a very simple example would be: you flip a coin, or you roll a die, or you draw a card from a deck. So those are the kinds of things that we can run an experiment and exactly one of various possible outcomes will occur. So having said that, I should say what an outcome is. An outcome is one of the things that can happen in an experiment. Outcomes are also known as simple events or sample points. So all of those words are synonymous. We use them interchangeably. Simple event, sample point, or outcome. If you put all the possible outcomes together, that's called the sample space. So the sample space is essentially the set of all things that can happen in an experiment. So if you're just going to flip one coin, for example, the sample space is head and tail, because those are the two things that can happen. You can get a head or a tail. The sample space is also known as probability space. So those words we'll use interchangeably: probability space or sample space. You might, if you're studying probability with your own textbook, they might use the word sample space, they might use the word probability space, but those mean the same thing. Finally, an event is a subset of the sample space that is a set of some of the outcomes. So an event means, for example, if we're going to pick a card from a deck of cards, the event could be that we get a spade, because there are 52 cards in a standard deck and 13 of them are spades. So we collect all those 13 outcomes together and we call them an event. We often use the variable S to describe the set of all possible outcomes, so the sample space. And we often use the variable A, or sometimes A and B when we have multiple ones, to describe different events in that sample space. So we'll talk about the probability of an event A occurring when we run an experiment. So let's figure out how we compute the probabilities. The way we do that, if we have an event, is assuming that these are things that we can count and everything's nice and finite. First of all, we count the number of outcomes in the sample space S. So you count all the possible things that can happen in an experiment. If you're flipping a coin, the only two things that can happen are head and tail. So you just count the head and the tail. You get two possible outcomes. If you're drawing a card from a deck, there's 52 different things that can happen, because you could get the ace of spades or the two of spades up to the king of spades and so on. There's 52 different cards that you might draw. So those are all the outcomes. And then to calculate the probability of an event, you want to count the number of outcomes in that event. So for example, if you were drawing a card from a 52 card deck and you wanted to calculate the probability of getting a spade, so P of getting a spade when you draw a single card from a deck, well, there's 52 possible outcomes. There's 52 possible cards that you could draw, and 13 of them qualify as being in that event. So there are 13 possible outcomes which would give you spades. And then, of course, you can reduce the fraction 13 over 52, and you find that the probability of getting a spade is 1 over 4. So that's not very surprising. So because of this nature of probability, you're counting things all over the place. There's a lot about counting outcomes, counting events. And so a great deal of our early focus in the probability course is going to be on it's going to have a combinatorial flavor where we try to count different events and count different sample spaces. So you'll see that some of the problems that we study today and in some of the other early lectures are all about counting different things, different complicated counting techniques. So you'll get the hang of it as we get into it and as we start to practice it a little more. So our first example is to roll 2 dice and to see if the sum showing on the 2 dice is 10. Remember, these are standard dice, so they're labeled 1 through 6 on the 6 sides, and we want to see if the sum is going to be 10 between the 2 dice. So we want to identify the experiment, we want to list all the possible outcomes, and the event that we're interested in, which means the subset of outcomes that would give us 10. And we want to find the probability of the event, so the probability that we're going to get a 10 when we roll 2 dice. So this is a pretty standard probability problem. The experiment here is just roll the 2 dice. So we're rolling the dice, roll the 2 dice. The outcomes are all the different possible ways that the 2 dice can come up. And it's very helpful here if you have a mental image of the dice being distinct. Maybe think of one of them as being red and one of them as being blue. So think of you're rolling a red die and a blue die. And so let's think of all the different combinations that can arise there. So the red die could be 1, 2, 3, 4, 5, and 6. And then the blue die could be 1, 2, 3, 4, 5, and 6. And then they're all the different possible combinations of the 2 dice there. So the red could be 1, and the blue could be 1. The red could be 1, and the blue could be 2. The red could be 1, and the blue could be 3. And so on. So there's 6 possible combinations in that first row there. Then there'll be 6 possible combinations in the second row, third row, fourth row, fifth row, all the way up to, you could get 6 on both dice. You could get the red die being 6 and the blue die being 6. So there are 36 possible outcomes in the set there. So our sample space here is all those possible outcomes. We could have a red 1 and a blue 1. We could have a red 1 and a blue 2. Oops, I meant to make that 2 blue. Let me see if I can make it look more blue there. There we go. And all the way up to a red 6 and a blue 6. So we have 36 possible outcomes in this experiment, possible combinations of numbers on the 2 dice. So that's our sample space, all the possible outcomes. Now we want to identify the event we're interested in. So the event here is that the 2 dice sum up to 10. So let's think about which of those possible outcomes would give us a sum of 10. Well, you could get a red 4 and a blue 6. You could get a red 5 and a blue 5 because those add up to 10. Or you could get a red 6 and a blue 4 because those also add up to 10. So 3 of those combinations between red and blue add up to 10. So that is the event we're interested in. So we now know what our event is, and we now know what our sample space is. So let's figure out what the probability is. The probability of our event A is the number of outcomes in A divided by the total number of outcomes in our sample space, the total number of things that can happen, outcomes in S. And we've calculated both of those. We looked at the event A and we saw that there were 3 outcomes that give you a sum of 10. In S, there are 36 possible outcomes. And so that simplifies down into 1 over 12. So that's the probability of rolling a 10 when you roll 2 dice together. Let me flag that. That's our final probability there. Probability. So just to recap here, what we did was we identified our experiment, which was rolling the 2 dice. We listed all the possible outcomes. All the possible outcomes was this chart right here. There are 36 possible outcomes, possible combinations of what might be showing on the red die with what might be showing on the blue die. So I didn't actually list all 36 because that would be too cumbersome, but we know there will be 36 of them. And then we had to identify the event, which is that our 2 dice add up to 10. So there are 3 possible outcomes. 3 of those combinations add up to 10. Let me mention right here a place that often confuses students when they're first starting to study probability. People wonder why it sort of looks like 4, 6 got listed twice and 5, 5 only got listed once. And that's true. But that's because there's 2 different ways you could get a 4, 6. You could get a red 4, blue 6, or you could get a red 6, blue 4. So that one really gets listed twice. 5, 5, there's only one way you can get it, which is to get 5s on both of the dice. So there really are 2 ways to get a 4 and a 6. There's only one way to get a 5 and a 5. In fact, this is even reflected when people roll dice in casinos in the game craps. People talk about getting 10 the hard way, which means getting a 5 and a 5, because that's harder than getting a 4 and a 6, because there are 2 ways to get a 4 and a 6. So we listed our event. We found 3 outcomes there. And then the probability of our event is just the number of outcomes in the event and the number of outcomes divided by the number of outcomes in our sample space. So there are 3 outcomes in our event. We counted those, and there were 36 in our sample space. 3 over 36 reduces down to 1 over 12. So let's keep going. And in our second example, we're going to flip a coin 3 times and see if we get exactly 2 heads. And again, we want to identify the experiment, all the possible outcomes, and the event we're interested in, and then we want to find the probability of the event. So the experiment here is flipping the coin. The experiment is to flip the coin 3 times. All the possible outcomes are all the possible combinations of heads and tails that we can get. So the possible outcomes here, I'm just going to try to list them systematically. We could get, let me call this S because this is the sample space that we're listing right now. S is, we could get head, head, head. We could get head, a head, and then a tail. We could get a head, a tail, and then a head. A head, and then a tail, and then another tail. We could get a tail, a head, and a head. Get a tail, head, tail. Tail, tail, head. Or tail, tail, tail. So there are 8 possible outcomes here. That's really coming from the fact that 2 times 2 is, or 2 times 2 times 2 is 8. Because each time you flip the coin, there are 2 different things that can happen, but then you multiply those possibilities as you go along, so you get 8 possible combinations of flips there. So those are the outcomes that we're interested in. Well, that's the entire sample space. The event that we're interested in is that we get exactly 2 heads. So exactly 2 heads. I want to figure out which of those outcomes satisfies that criterion. So exactly 2 heads would mean certainly HHH doesn't, but HHT does. And HTH does. Head, tail, head. And then down there I see tail, head, head. Tail, head, head. And that's it. Those are all the only ones there are that have exactly 2 heads. So our event just has those 3 possible outcomes that satisfy the requirement. And then finally, we want to find the probability of the event. The probability of A is the number of outcomes in A, divided by the total number of outcomes in our sample space, in our probability space, outcomes in S. And so in A we had 3 possible outcomes, in S we had 8, and that doesn't reduce, so our final answer there is 3/8. That's the probability of getting exactly 2 heads when we flip a coin 3 times. So let me make sure that all the steps there are clear. We wanted to identify the experiment, so identifying the experiment is just flipping the coin 3 times. We wanted to list all the possible outcomes, and so I listed them in order here. I kept track of the first flip, the second flip, and the third flip. And so there were 8 possible outcomes. 8 possible outcomes. And remember I said that came from 2 cubed because it's really, there are 2 things that can happen on the first flip times 2 things that can happen on the second flip times 2 things that can happen on the third flip. Exactly 2 heads, I just scanned through that list of outcomes and I identified the ones that have exactly 2 heads. The first one has 3 heads, so that doesn't count. The second one and the third one both have exactly 2 heads. The 5th one here has exactly 2 heads, and that's why I took those and put them into the set describing the event that we're interested in. Finally, the probability of that event is just the number of outcomes in A, which is 3, and divided by the number of outcomes in S, which is 8. So that's where we got the probability being 3/8 there. For our next example, we're going to be drawing cards from a deck. So we're going to take a standard 52 card deck, and we're going to keep drawing cards until we find the ace of spades. So the question is, what's the probability that it will take us between 20 and 30 cards, including 20 and 30. That's what inclusive means. When it says inclusive, it means you include those starting and ending values. It says identify the experiment, all the outcomes, and the event that we're interested in. So the experiment here is just drawing the cards. We're drawing the cards. Don't know how long it's going to last because we might get the ace of spades on the very first pick. Drawing the cards. Or if we get unlucky, we might have to draw 51 cards and then get the ace of spades on the very last pick. So the set of possible outcomes really depends on where we get the ace of spades. So we could get the ace of spades on the first pick if we were very lucky. We could get it on the second pick. That would still be pretty lucky if we got the ace of spades on the second pick. Anywhere up to the 52nd pick would be our worst case scenario if we got the ace of spades as the very last card that we draw. Remember, we said without replacement, which means after we draw a card, we're not putting it back in the deck. So I know for sure that eventually I'm going to find the ace of spades. If I were putting cards back in the deck, I might potentially never find the ace of spades because I could keep drawing forever and just keep drawing new cards. Our event here is that we're going to draw between 20 and 30 cards. So our event would be that we get the ace of spades on the 20th pick, or possibly on the 21st pick, or all the way up to the 30th pick. So that's our event there. That's our A. Generally use A and B for events, and we always use the letter S for the sample space. The probability of A, that's what we're really trying to calculate here, is the number of outcomes in A divided by the number of outcomes in S. So we just need to calculate that. The number of outcomes in S, we already said there's 1 pick up to 2 picks up to the 52nd pick. So there are 52 possible outcomes in S. And if we look at A, 20, 21 up to 30, there's actually 11 of those outcomes because we're counting the 20 and the 30 on both ends. So it's 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 is 11 outcomes in the event A. So we actually have 11 outcomes, not 10. It might seem like there's 10, but there's that extra one on the end. So that's our probability of drawing the ace of spades somewhere between the 20th card and the 30th card. So let me go back over that and make sure everything's clear. The experiment here is drawing the cards. We're drawing the cards one by one. We might just draw a single card. We might end up drawing all the way to the 52nd card, because remember, we stop whenever we get the ace of spades, and we aren't putting cards back in the deck. That's a very key point to mention here. The outcomes are that we could get the ace of spades on the first pick, the second pick, all the way up to the 52nd pick. So that's 52 possible outcomes in our sample space. The event that we're interested in, according to the problem, is that we might get the ace of spades on the 20th pick, the 21st pick, or all the way up through the 30th pick. So there's 11 of those possibilities that we're interested in to satisfy the requirements of the problem. So when we're calculating the probability, we divide those numbers together. The number of outcomes in the event we're interested in divided by the total number of outcomes just gives us 11 over 52. So in example 4, it's the same experiment as before. We're going to roll 2 dice. I think we saw that in example 1. This time we want to see if the sum is a prime number. And again, we're going to identify the experiment, all the outcomes, and the event we're interested in. And we're also going to find the probability of the event. So the experiment, just like before, is to roll 2 dice. I think this was example 1 before. Yeah, that was example 1. So our experiment is the same thing. We're going to roll 2 dice. But now the outcomes, those are also the same as before. Those are all the possible combinations you can get when you roll 2 dice. And again, it's very helpful to think of the dice as being red and blue. So you can get a 1, 2, 3, 4, 5, and 6 on the blue die. You can also at the same time get 1, 2, 3, 4, 5, and 6 on the red die. So in terms of combinations, you could have red 1, blue 1, you could have red 1, blue 2, and so on. There are 36 possible combinations, all the way down to red 6, blue 6. And so we want to figure out, so that's my set of outcomes. That's my sample space there. 36 possible combinations there. This is S. And we want to identify the event here. The event here is that the sum showing on the 2 dice is a prime number. So let's figure out which of those combinations could give us a prime number. I'm going to go to a new screen for this because it takes a little bit of calculation. So the event here is, I'm going to call it A, the set of combinations for which the sum is a prime number. The sum is prime. And let's remember our prime numbers. The prime numbers, well, between 2 and 12, because those are the only possible combinations you can get by rolling 2 dice. You can get a 2. 2 is prime. 3 is prime. 5 is prime. 7 is prime. And 11 is prime. So those are all the possible totals we're looking for. And I want to figure out which combinations will give me those possible totals. So to get a 2, I could roll a 1 on the red die and 1 on the blue die. That would give me a total of 2. And that's the only possible combination that does give me a total of 2. To get a 3, I could get 1 on the red die, 2 on the blue die, or I could get a 2 on the red die and a 1 on the blue die. To get a 5, I could roll a red 1, blue 4. I could roll a red 2, blue 3. Oops, that was supposed to be blue. Let me make that blue. Blue 3. I could roll a red 3, a blue 2, Or I could roll a red 4, a blue 1. So there's 4 possible combinations that would add up to 5. For 7, I could roll a red 1, a blue 6. I think I'm going to stop switching colors back and forth because it's kind of slowing me down here. I could roll a red 1, blue 6, red 2, blue 5, red 3, blue 4, red 4, blue 3, red 5, blue 2, or red 6, blue 1. So there's 1, 2, 3, 4, 5, 6 combinations that could give me a total of 7. To get 11, I could roll a red 5 and a blue 6, or a red 6 and a blue 5. So those are the ways that I could get 11. There's a very nice way to keep track of these. Instead of trying to list all these and not being really sure if you've got them all, let me remind you of what the sample space looked like. So for blue, we could get 1, 2, 3, 4, 5, 6. For red, we could get 1, 2, 3, 4, 5, and 6. And for red, we could get a red 1, blue 1. We could get a red 2, blue 1. We could get a red 1, blue 2, and so on. We could fill in the rest of this chart. But when we're trying to list totals, if we look at the total of 2, let me circle that in green here, its only way to do it is by getting a 1, 1. That's a total of 2. If we want a total of 3, we could get a 2, 1 or a 1, 2. So those are the ways that you get a total of 3. A total of 5 would be, you could get a red 1, blue 4, a red 2, blue, I wrote that in the wrong place there. That would be a red 4, a blue 1. You could get a red 3, blue 2. You could get a red 2, blue 3. Or a red 1, blue 4. So what you get here to get a total of 5 is this sort of diagonal stripe on the table. It's 2 stripes below the stripe for 3 because 5 is 2 bigger than 3. To get a 7, again, you're going to get a diagonal stripe on the table 2 places below. So you're going to get 6 outcomes across this diagonal stripe. So there'll be 6 outcomes in there, all the ways where the red and the blue can add up to 6. And finally, to get 11, there's you can get a red 6, blue 5, or a red 5, blue 6. So there's a shorter diagonal stripe there. This is to get 11. This was to get 7. And so we can look at these diagonal stripes and the lengths of these stripes to calculate the total probability of this event. We just add up all the lengths of those stripes. So that's kind of a good way to check that we haven't overlooked any possibilities here. So that's our event. Let's calculate the probability now. The probability of A is equal to the number of outcomes in A divided by the number of outcomes in S. And now I need to count up the total number of outcomes in A. So if I look at 2, I see 1 possible outcome. If I look at 3, I see 2 possible outcomes. 5, I see 4 possible outcomes. 7, I see 6 possible outcomes. 11, I see 2 possible outcomes. And again, I can check these numbers by looking at the lengths of these stripes over here. So 7 has a stripe of 6, 5 has a stripe of 4, 3 has a stripe of 2, 2 has a stripe of 1, 11 has a stripe of 2. So those correspond to these numbers here. And then if I just add all those numbers up, I see 2 plus 6 is 8, plus 4 is 12, plus 2 is 14 plus 1 is 15. So I get 15. And then remember the total number of outcomes in S, that was the total size of this chart, which was 36. Looks like 15 and 36, I can reduce that if I take a 3 out of each one, reduces down to 5 over 12. So that's my probability. If I roll 2 dice, what's the probability of getting a prime number? The answer is 5 out of 12. So let me remind you of everything we did there. First, I made a chart of all the possible outcomes. I didn't fill them all in because it would have taken too long, and I kind of got the idea of what the shape would be. But there are 36 possible outcomes depending on the 6 possibilities for the red die and the 6 possibilities for the blue die. And then I identified my event, which is that the sum is prime, which means the sum has to be 2, 3, 5, or 7. So I looked at my chart and I tried to list all the outcomes that would lead to the sum being 2, 3, 5, or 7. So that's where I got 1, 1 for 2, 2 possibilities adding up to 3, 4 possibilities adding up to 5, 6 possibilities adding up to 7, and then just 2 possibilities adding up to 11. And to find the probability, I need to count up all those possibilities. So I added up all those numbers. That's what I was doing over here. Add them all up to get to 15. That's where this 15 comes from. And then divide by the total number of outcomes in the sample space, which is 36. And then 15 over 36 reduces down to 5 over 12. So that's how we got that probability. So for example 5, it's a little bit different from some of the others. We're going to flip a coin repeatedly until we get a head. And I want to calculate the probability that we're going to flip at least 3 times. So the idea is we keep flipping this coin over and over again. As soon as we see a head, we stop, and then that's the number of flips that we've done in total. What's the probability that that number will be 3 or greater? So let's identify the experiment and all the outcomes and then find the probability of that event. So the experiment here is just flipping the coin. Is just flipping the coin over and over again, and then as soon as we see the first head, we stop. The outcomes. Now this is a little different from all of our examples so far, because what can happen here is, well, we could get a head right away on the first flip. So that's our first possible outcome, is that we get a head right away. Or we might get a tail on our first flip and then get a head, and then we would stop. Or we might get a tail and then another tail and then get a head, and then we would stop. We might get 3 tails and then get a head, and then we would stop. And we don't really know how long this is going to go. There's no ceiling on how long this is going to go. It could go forever. So I can't just list all of these outcomes because there's infinitely many. It could go on indefinitely. The event that we're looking for is that we have at least 3 flips. So that's A is the set. A single flip getting us a head wouldn't qualify. A tail and a head would not qualify. It would be tail, tail, head. That would be 3 flips. Tail, 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 head. That would be more than 3 flips. Tail, 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 head. That would be more than 3 flips. So it's anything that has 3 flips or more. So we want to identify the probability of that event. Unfortunately, we can't do this one by counting because we have an infinite number of outcomes in our event. We have an infinite number of outcomes that can happen from the experiment. So we can no longer use our counting formula from before. So instead, let me introduce a new way of calculating it. So our way of calculating the probability is we can add up the probabilities of each of these individual outcomes in our event. So it's the probability of tail, tail, head, plus the probability of tail, 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 head, plus the probability of 4 tails and then a head, and so on. And this is going to be an infinite sum. We're going to have to add all these up forever. So we'll have to do something clever at some point. Tail, tail, head. To get a tail, tail, head, well, there's a 1/2 chance that you'll get a tail right away, and then there's a 1/2 chance that you'll get another tail, and then there's a 1/2 chance that you'll get a head. So put those together and you get 1/8. Tail, 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 head. Again, there's 50% chance of getting a tail, 50% chance of getting another tail, 50% chance of getting another tail, 50% chance of getting a head after that. So it's 1/2 times 1/2 times 1/2 times 1/2. Multiply all those together, you get 1/16. Here you'll be multiplying together 1/2 to the 5th, which is 1 over 2 to the 5th is 32. And so we have to add all those up. So 1/8 plus 1/16 plus 1 over 32. And this is an infinite series. So now you have to remember something from your Calculus 2. If you don't remember how to deal with infinite series, we've got some great lectures here on Educator.com on second semester calculus, Calculus Level 2, taught by a great instructor. And there's a lot of work in there in adding up infinite series. So here we're going to apply that. This is actually a geometric series. And with a geometric series, you need to identify the common ratio. Here, the common ratio, what we're doing from each term to the next is we're multiplying by 1/2. So each term is 1/2 as big as the previous term. The important thing here is that 1/2 is less than 1, because that tells us when a geometric series converges. It converges when the common ratio is less than 1. So it does converge. And we learned back in those lectures on Calculus 2, the sum of an infinite geometric series, I'm going to write it in words, is the first term over 1 minus the common ratio. 1 minus the common ratio. In this case, our first term is that 1/8 right there. So it's 1/8 over 1 minus the common ratio, which is 1/2. So 1/8 over 1 minus 1/2, which is 1/8 over 1/4. Do a little flipty-flipty here, and we get 4 over 1 times 1 over 8. Sorry, that's 1 minus 1/2 is not 1/4, it's 1/2. So when we do the flipty-flipty there, it's 2 over 1 times 1 over 8, which is 1/4. So that's our probability of having to flip this coin at least 3 times in order to see the first head. So I'm going to go back and calculate this a different way. We'll see a different way to solve this problem, but I'm going to do that on the next page. So let me recap how we calculated it using this method first. So our experiment was just flipping the coin here. The possible outcomes are all the possible strings of heads and tails that we can see. Remember, we stop as soon as we see the first head. So if we get a head right away, we stop. If we get a tail, we keep flipping, and then we get a head, we stop. If we get 2 tails and then a head, we stop after that head. If we get 3 tails and then a head, we stop after that head, and so on. So those are all the possible outcomes. The event we're interested in was that we flip at least 3 times. So I listed all the outcomes that have 3 or more flips. And then to find the probability of that, we can't count these things anymore because there's infinitely many of them. So instead we have to find the probability of each one. So the probability of tail, tail, head is 1/8 because it's a 1/2 times a 1/2 times a 1/2. Tail, 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 head is 1/16 because there's you have to predict the flips 4 times in a row to get that right. Here, tail, 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 head, you would have to predict 5 flips in a row, so you'd have a 1/2 chance of each one, so 1/32. Adding all those up, we notice that we get a geometric series, and our common ratio, what we're multiplying by each time, is 1/2. Now you got to remember the sum of a geometric series, which we learned back in Calculus 2, in Level 2 Calculus, is the first term in the series divided by 1 minus the common ratio. So that's where I got 1/8 is that first term. That's where that came from. The common ratio is that 1/2. 1/8 over 1 minus 1/2 simplifies down to 1/4 is my probability. Now I'm going to calculate this a different way. So let me show you how you could have done that, in fact, without summing up a geometric series. So here's an alternate solution for that one, the same one as before. Alternate solution. Is to find the probability of A is equal to, well, we can calculate the complement of A, which means the opposite of A. So that's the complement. A bar means the complement of A, the opposite of what we're looking for, and then do 1 minus the probability of the complement of A. So let's figure out what the complement of A is. Remember, A was the set of outcomes that have at least 3 flips. So that was tail, tail, head, tail, 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 head, and so on. The complement of A is just the outcomes that had 2 or fewer flips. So that could be if you get a head right away, or you get 1 tail and then a head. And that's it, because anything else would have 3 or more flips. So the probability of the complement of A is the probability of getting a head immediately plus the probability of getting a tail and then a head. The probability of getting a head right away on the first flip is 1/2. Probability of getting a tail and then a head is 1/2 times 1/2. So we get 1/2 plus 1/4, which is 3/4. That was the probability of the complement of A. So the probability of A is 1 minus that, 1 minus 3/4, which is 1/4. Of course, that's the same answer we got before, but using quite a different strategy. So it's kind of reassuring. They ought to be the same answer, but it's nice to see when they check each other. So let me make sure that that's still clear. What we did here was we calculated the complement of A. That means everything that is not inside A. So it's sort of the opposite set from A. A was tail, tail, head, tail, 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 head, all the strings with 3 flips or more. So the complement is all the shorter strings. That's just getting a head or getting a tail and a head. And the probability of that is, well, probability of just getting a head on the first flip is 1/2, because you flip 1 coin. What's the chance of getting a head is 1/2. The probability of getting a tail and then a head, it would be 1/2 times 1/2, because you got to get 2 flips the way you're predicting them. Add those up, you get 3/4, and then we subtract that from 1 because we're using this formula here. So 1 minus 3/4 is 1/4. That's the probability of the experiment going for at least 3 flips. So in our last example here, we're going to draw a 5-card poker hand from a standard 52-card deck. And the question is, what's the probability that we draw all spades? So we want to identify the experiment, all the outcomes, and the event that we're interested in. So there's a lot of possible outcomes for this experiment. We're going to be learning some new notation in the context of this example, because it's going to introduce something that we're going to be studying later. So we're going to learn about combinations a little bit in this example. So the experiment here is drawing the cards. Experiment is drawing the cards. Drawing the cards. The set of possible outcomes is all the different ways to draw 5 cards from a standard 52-card deck. And this is a little tricky to count, so let me show you how it works out. Think about it. We're drawing from a 52-card deck. There are 52 ways we could draw the first card. After we've drawn that first card, there are 51 cards left in the deck. So there are 51 choices we could make for the second card. Then there are 50 choices left for the third card. And then 49 choices for the fourth, and 48 choices for the fifth. So that seems like there's this very large number of ways to get a particular poker hand. However, once you've got the 5 cards in your hand, we don't care what order they're in, which means that say you get, say the cards you draw are 1, 5, 3, a jack, and an 8. And I'm not even going to worry about the different suits, the clubs or spades or hearts or diamonds. But suppose you get a 1, 5, 3 jack or an 8. Well, you could also have drawn the jack and then the 3 and then the 1 and then the 5 and the 8. And once those cards are in your hand, that looks like the same poker hand because you can shuffle them around in your hand. So what we did when we were counting all the different ways to draw the 5 cards is we counted these 2 poker hands separately, even though they're really the same poker hand. So the problem is that we're overcounting. We're counting the same poker hand multiple times. And so we have to take this answer and we have to divide by something, and we have to divide by the number of ways that each poker hand got counted. So now let's just think about a particular poker hand. Let's think about this one in particular, 1, 5, 3, jack, 8. And let's think about the number of different ways that that poker hand was counted in our original list. So just think about how many different ways could you order those 5 cards. Well, there's 5 choices for which card could have been first, assuming that we're talking about that particular hand. So there's 5 ways, the 5 choices for the first card. Once you pick that first card, there are 4 choices left for the second, and then 3 choices left for the third, and then 2 choices left for the fourth, and then the 5th card would be fixed. Remember, we're talking about a particular poker hand, like 1, 5, 3, jack, 8. So we're talking about those 5 cards. How many different ways could those 5 cards be rearranged, and how many different ways did they get counted in this original list? So the answer is 5 times 4 times 3 times 2 times 1. So we have to divide that out of our list because each poker hand, each group of 5 cards got counted. Well, 1 times 2 times 3 times 4 times 5 is 5 factorial ways in our original list. So we have to divide out by 5 factorial in order to get an accurate number of the different possible poker hands. So that's the total number of outcomes. There's a clever way to simplify this using factorials. Notice that the denominator here is 5 factorial. The numerator is 52 times 51 times 50 times 49 times 48. That looks like we're starting to build up 52 factorial, but what's missing there is 47 times 46 on down to 1. And if I just multiply those on, I have to divide them out again. So 47 times 46 on down to 1. And so another way to write that is as 52 factorial divided by 47 factorial. So that's another way to list the total number of hands. And this is actually something we're going to learn about in the next lesson. The total number of ways to choose 5 cards from 52 is, the notation we're going to use is 52 choose 5. And there's some other notation along with this notation. It's a little confusing because different textbooks use different notations, but C of 52, 5. And what it means is this factorial formula. So this is read 52 choose 5. You read that as 52 choose 5. And what it means is this factorial formula. You expand it out by doing 52 factorial divided by 5 factorial, and this 47 factorial really came from the fact that 47 is 52 minus 5. That's where that came from, because that 47 came from this 47 here, which came from this 47, which came from the fact that we had already used up 5 of the factors of 52 factorial there. So the number of outcomes here is 52 choose 5. This is our new notation, 52 choose 5. And it's the way you calculate it is as 52 factorial divided by 5 factorial divided by 47 factorial. So let me recap this because we're going to have to keep going on the next slide here. I haven't even talked about the event that we're interested in yet. Our experiment is drawing the cards. The number of ways to draw the cards, well, there's 52 ways to get your first card. Once you've drawn that card, there's only 51 cards left in the deck. So there's 51 ways to get the second card. Now there's 50 cards left in the deck, 50 ways, 49, 48. But the problem is that that overcounts because you could get the same poker hand in different possible orders. So in order to fix that, we looked at a single poker hand, sort of a typical poker hand, and we figured out that the number of ways that that could have been ordered was 5 times 4 times 3 times 2 times 1. So that's why we had to divide out by 5 times 4 times 3 times 2 times 1. It's because each poker hand got counted that many ways in our initial list up here. So each poker hand, we sort of overcounted by a factor of 5 factorial. So that's our number of outcomes, but then as a clever way to write the numerator, we wrote that as 52 factorial divided by 47 factorial. So that's where this part of our answer comes from. The 47 comes from 52 minus 5, and then this 5 factorial is where we got that 5 factorial in the denominator there. So this is our new notation, 52 choose 5, and it's sometimes written with these elongated parentheses, and it's sometimes written with this capital C. C stands for combinations there. By the way, this 52 choose 5, it looks like a fraction. It's not a fraction in the sense it's not the same as 52 over 5. So don't put the bar there. Don't turn it into a fraction because those are totally different things. All right, so that's just the number of outcomes. We still need to count all the outcomes in the event that we're interested in. The event was that we draw all spades. So let's try and figure that out. I'll try and figure that out on the next slide. But in fact, it'll be fairly easy if you remember the strategy that we used here. Remember that 52 choose 5 is all the ways you can draw 5 cards from 52 cards total. So keeping going with this example, our event is ways to get a poker hand, a 5-card poker hand of all spades. And here's the clever way to think about it. Remember how we drew our hand in the first place, the 52 choose 5? Think about if they're all going to be spades. So if they're all going to be spades, then we're really saying it's the number of ways to choose 5 spade cards, 5 spades, out of how many spades are there total? Well, there's 13, the ace through the king of spades, out of 13. So, according to our logic before, that's exactly 13 choose 5. So if we wanted to express that in factorials, that's 13 factorial divided by 5 factorial divided by 13 minus 5 factorial, which is 13 factorial divided by 5 factorial times 8 factorial. So that's our number of ways to choose 5 spades out of, there's only 13 in the deck, so that's the number of ways that we can get 5 spades. So our probability of A is the number of outcomes in A divided by the number of outcomes in S. And so we already calculated both of those. It's 13 choose 5 divided by the total number of poker hands we can get is 52 choose 5. So that's, we could simplify that down if we wanted. 13 factorial divided by 5 factorial times 8 factorial. And we already saw above that 52 choose 5 is 52 factorial divided by 5 factorial times 47 factorial. And we could simplify that a bit farther. We could cancel the 5 factorials and flip up the denominator. So 13 factorial divided by 52 factorial. Well, 13 factorial divided by 8 factorial times 52 factorial. And then the 47 would flip up to the numerator, and the 5 factorials would cancel. So I'm going to make no attempt to try to actually calculate that as a number. It would be a very small number. But that is our probability if you draw 5 cards out of the deck that all 5 cards will be spades. So that's the end of our 6th example there. Let me recap just quickly what we did on this second slide here. Our event was the number of ways to get a poker hand of all spades. And using our strategy from before, that's 13 choose 5. Remember, we learned that notation on the previous slide. If you don't believe that, another way to think about that is to say, well, how many ways can we get all 5 spades? So if you're choosing 5 spades, there's 13 ways to get the first one. Once you've picked 1 spade, there's 12 ways after that to get the second one. 11 ways once you've picked the first 2, times 10 times 9. So there's your 5 spades. But that overcounts because, again, the 5 spades could have come in any order. So the number of possible orders they could have arrived in is 5 times 4 times 3 times 2 times 1. And so that simplifies, well, I don't know if it really simplifies, but we have 5 factorial in the denominator. And the numerator, we can cleverly write it as 13 factorial divided by 8 factorial because we're multiplying all the numbers down from 13, but we're cutting off all the ones down from 8. So we could get that as 13 factorial divided by 8 factorial. So that's another way to get to that same answer there for the event that we're interested in. And then to find the probability, we just take the number of ways to get our event divided by the total number of outcomes. 13 choose 5 divided by 52 choose 5. And we get a kind of cumbersome expression involving factorials as our answer. So that wraps up our last example, and that wraps up our introductory lecture here on Educator.com for probability. So we went over some terminology. We practiced some basic probability using counting techniques. In the next few lectures, we'll develop these counting techniques farther and solve some more complicated probability problems. So I hope you'll stick around for that. These are the probability lectures here on Educator.com, and my name is Will Murray. Thanks. Bye-bye.